What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video we're going to prove some important trig limits that you're going to see a lot in calculus. Here they are, and let's go ahead and jump right into it. We're going to prove the first one. The limit as x approaches 0 of the sine of x over x equals 1. And in this proof we're going to use something called the squeeze theorem, or sometimes called the sandwich theorem. And if you are brand new to this, I'll have a link pop up above. But what the squeeze theorem allows us to do is we can take a function we're trying to find the limit of, and we can bound it between two other functions, g and h. And so we come up with a string of inequalities that's true for all x near a, which is the number that x is approaching, except possibly at a itself. We don't care what's happening at a, or 0 in this case, just what's happening near it around some interval. Okay, so if we can set this up, if we can bound the function f, and if we can have it to where these bounding functions g and h have the same limit, that we can conclude that the limit of this bounded function f that we're trying to find is also that same limit. All right, so here's our proof outline. Here's what we're going to bound sine of x over x with, and that is cosine of x and 1. This string of inequalities is true for all x in this union of intervals. So this is what it means to be near 0 except at 0 itself. We actually can't compare sine of x over x to anything at 0 because it's undefined, and it wouldn't make sense to say undefined is greater than or equal to or less than or equal to anything else. So this is what it means to be near 0 but not necessarily at 0 itself. And then what we have is these bounding functions cosine of x and 1 both have a limit of 1 as x approaches 0. And so since these two things are true, we can say by the squeeze theorem, the limit as x approaches 0 of sine of x over x equals 1. So I call this a proof outline because you should be reading this and be very apprehensive due to this. This should not be obvious to you. It is absolutely not obvious to me that this is true for x values in this interval. And if it is obvious to you, then you should close out of this page and probably look for a math PhD program because you might actually be a genius. So what we're going to do is we're actually going to prove that this string of inequalities is true for all the x's in this union of two intervals. And actually once we do that, then really we have our proof. We're just going to add in that proof in the beginning here. We're going to justify that this is true, and then this can be the rest of the proof. Since this is true, and this happens because hopefully we can state this without justification. This part should be obvious. That should be clear. By the squeeze theorem, we have our limit. All right, so let's jump into proving that this string of inequalities holds on the union of these two intervals, and we're going to break up that union into two different intervals. We're going to start for x values near 0 but greater than 0. And then we're going to look at x values near 0 but less than 0, so that negative pi over 2 to 0 interval next. And the reason we're breaking it up is because we use a geometric argument here to prove this. And since we're using a geometric argument, we want to consider differences between, potentially having an angle in the first quadrant, which aligns with this interval, or a negative angle in the fourth quadrant, which aligns with the other interval. So let's start here. This is a geometric argument. I have x drawn here. It's in the first quadrant. We know that because we're restricting from 0 to pi over 2, which is 90 degrees. This is a portion of the unit circle, so I know this point is 1, 0, because the radius of the unit circle is 1, and I know any point on the unit circle can be defined as cosine of x, sine of x. This height being tangent of x, we're going to get to that here in a second. That's probably not obvious. It wasn't to me. And here's our argument. Let me just break it down. It's comparing the areas of three regions. First, we're going to look at the area of this blue triangle. I'm drawing the base right here. So this dotted line is the height. And what we could say is that the area of this blue triangle is definitely less than the area of this sector of the circle. So I'm drawing the sector here, right? So the sector includes the triangle plus the area of whatever this little region is. That's the area of the whole sector. And hopefully that is obvious, that the area of that sector is bigger than the area of this blue triangle. What we can also say is that the area of this larger pink triangle, so I'm outlining the whole thing here, is bigger than the area of the sector, which is bigger than the area of the blue triangle. So now we have three quantities that we compare the areas of that allow us to set up a string of inequalities comparing three quantities. So first, the smallest area is the area of this triangle. The area of a triangle is 1/2 times base times height. So we're going to write 1/2 out here. And what is the base? Well, that's this length here, and that's 1 because we're on the unit circle. That's the same as the radius of the unit circle. So 1/2 times base. And then what is the height of the circle? That's this dotted line, and that aligns with the sine of x. That tells us the height on the unit circle. That's the y coordinate of a point on the unit circle. So we have 1/2 times 1 times the sine of x, and that's the area of this blue triangle. Now let's look at the area of this sector, and there is a formula for this. I think it's 1/2 r squared theta, where theta's in radians. So you can use the formula, but that might not even be right. I really don't use the formula. I just think about this being a piece of the area of the circle. So how much of a circle is this? Well, x radians out of a total of 2 pi radians. And then the area of a circle is pi r squared, and the radius in this case is 1. So pi times 1 squared. And this can be simplified. We'll do that in the next step, okay? So either way, you get the same thing. Whether you use the formula or you think about this being a portion of the area of the full circle. I like to do the latter. Either way, you end up with the same thing. All right, now what about the area of this pink triangle here? And this is where it gets a little weird because I have this tangent of x written here. And y in the world is the height of that, the tangent of x. And here's the basic idea is that when we have a right triangle like this, let me draw one down here. When we have a right triangle like this and we draw a straight vertical line down, what it does is it creates two similar triangles. So let me use a different color. This triangle here, this smaller triangle, is similar to this larger triangle. So similar means it has all the same angles, and it means we have these equivalent ratios between sides, okay? So let's go back and label this tangent of x. Let's say we didn't know what this is. We were trying to find it, and we labeled it as question mark. I'm just going to use question mark. We could say that the ratio of the height and base of this blue triangle, so the height divided by the base of this blue right triangle here, this is the triangle that's similar to this larger pink triangle. Hopefully you see it. All right, so what is the ratio of the height and the base? Well, the height is the sine of x, and then the base here, that's the cosine of x. So that ratio is sine of x divided by the cosine of x, and that equals the ratio of the height and the base of this other triangle because they're similar, which is question mark, and the base is just 1, right? So dividing by 1, we can just get rid of that divided by 1. It's just itself. And so we could label this as just sine of x divided by cosine of x, but we know from our quotient identity that that's equal to tangent of x, and that's where that tangent piece comes from. Hopefully that makes some sense. All right, so what is the area of this pink triangle? As I get rid of this scratch work, because that's the biggest area here that we're comparing. It's bigger than the area of the sector and the blue triangle. And that's, again, just 1/2 times base times height. So we have 1/2 here times the base of this triangle, which is 1, times the height, which is the tangent of x. All right, now I have 3 expressions that I can compare. And notice we said less than, and I wrote less than or equal to. If a quantity is less than another quantity, then it's also less than or equal to the other quantity. So I just added the or equal to sign. It might feel weird. It's totally mathematically correct. I just added that so it aligned with our theorem, our squeeze theorem that we're going to use. All right, so now I can simplify some stuff here. What I have is the sine of x over 2 is less than or equal to, let's see, the pi's cancel here. That's just x over 2. And that's less than or equal to tangent of x over 2. And so now what I can do, remember, I'm trying to get this middle thing to look like sine of x over x. So the first thing I'm going to do is just multiply everything by 2, which I absolutely can do here. So I'm going to multiply everything by 2, and I get sine of x is less than or equal to x, which is less than or equal to tangent of x, which I'm actually going to write as the sine of x over the cosine of x. That's going to become helpful here in a second. All right, so how do I get this to look like this? We have x, I want sine of x over x, and really I can do 2 things. First, I can take the reciprocal of each expression, and then I can multiply each expression by the sine of x. So let's start by taking the reciprocal. What are our rules for taking a reciprocal of 2 sides of an inequality? And we need to check the signs, S-I-G-N, right, positive or negative of each of these expressions. When they are all the same sign, right, when they are all positive or all negative, then we could take the reciprocal of everything and we can just flip the inequalities. And you can convince yourself of this by comparing something like 3 is less than 4. Take the reciprocals, 1/3 is bigger than 1/4. So that's what happens when we have the same sign. We have to flip the inequalities. Okay, so are all these positive or all of them negative? Well, the sine of x is an angle in the first quadrant. That's positive. X is a positive angle. We know that it's in this interval in the first quadrant. And the sine of x is positive. Cosine of x is positive. So this is positive. Yes, they are all positive. And so we can take the reciprocal of everything and we just have to flip the inequality. So we have 1 over the sine of x, and I'm going to just flip the inequality. And maybe this looks weird to you. Maybe you prefer to like rewrite this at the end. Totally fine. Same thing. I am going to do that at the end. And we have cosine x over sine of x. And now our final step is to multiply everything by the sine of x. So now I have to think about the sine of x is positive. So when I do this, I don't need to flip any inequalities. And when I multiply everything by the sine of x, this becomes 1, right? We're going to have sine of x here, and those are going to cancel, and that becomes 1. And then we're going to have sine of x times 1, which is our sine of x over x. That's what we want. And then here we're going to have sine of x over sine of x. Those are going to cancel, and we're going to have cosine of x. So now I'm going to rewrite it in the proper order from least to greatest, because this is less than or equal to this, which is less than or equal to this. And I'm going to write everything simplified. And what I have is that the cosine of x is less than or equal to the sine of x over x, which is less than or equal to 1. And this is exactly what we wanted to show, and this is definitely true for all x in this interval, near 0 but bigger than 0. So now we're going to prove for the other interval, from negative pi over 2 to 0. And there's actually 2 different ways we can do this. The first way is just considering that all three of these functions are even functions. They are all 3 even functions. What's an even function? Well, graphically, it means that it has symmetry about the y-axis. So let's graph cosine, for example. It starts at its maximum, then it goes to its midline, then it goes to its minimum, then back to the midline, and it repeats this over and over, right? And it does the same thing over here. Midline, minimum, midline, maximum. And there's this reflection across the y-axis that occurs here. Okay, so that's one way to think about what an even function is. We can also write it in this way. What we could say is that f of x equals f of negative x. And I like that I have a graph here to relate this to. What this means is if I plug in any number into the function, let's say this is x, for example, if I plug that number in, whatever that output is, which is f of x, that's an output, that's this y value, that's the same output that I would get if I plugged in negative x into the function, right? So we can see how this kind of relates to our symmetry across the y-axis here. Okay, so cosine of x, that should be pretty clear. We just drew its graph that it's even. And so should the function f of x equals 1. That's literally a horizontal line, right? Of course, it reflects. No matter what we plug in, we get 1. It's really just this middle piece that's kind of unclear or not obvious to me that it's even. So what we can do to actually show it's even is we can compare. We know f of x, if this is the function, f of x is the sine of x over x, then we can say, well, what is f of negative x? Is that the same function, right? So we're going to plug in negative x as our input, and so in the denominator we have negative x. And actually sine is an odd function, which means that f of negative x is the same as negative f of x. So the sine of negative x is the same as the negative sine of x, and the negatives now cancel out. And what we've just shown is that f of x is the same as f of negative x, which means that this function is even. So since we have 3 even functions, and we just showed that this string of inequalities holds for all numbers between 0 and negative pi over 2, what we can conclude, because f of x equals f of negative x, is that this string of inequalities also holds, right, if we reflect across the y-axis for numbers between negative pi over 2 and 0. And hopefully that argument makes sense. I thought this was really cool. I found it online. If you don't like this way, there's actually another way to do it, which is doing the same type of geometric argument to show that this inequality holds on this interval. So now what we have is an angle in the 4th quadrant. It's a negative angle. And so this is a really weird thing to think about, because now we are still comparing the areas of the same 3 regions, but now the areas are flipped because they're all negative. And that might be a weird thing. Maybe in geometry you've thought area can't be negative, but when you take calculus, you're going to get to integration and you're going to learn about negative area. And one straightforward way to think about it is that 1/2 base times height, the height of this triangle is going to be negative. The sine of x is negative here. The height of this triangle, the tangent of x, that's going to be negative, right? And then we're going to end up here with what? X over 2, and x is a negative angle. So the area of this sector is going to also be negative. So all the inequalities flip. Since they are all negative, this biggest pink triangle here is the biggest negative area, which means that it's furthest to the left on the number line, right? So it's less than or equal to the area of the sector, which is less than or equal to the area of this blue triangle here. Hopefully that's making sense. We're flipping everything because now we have negative areas. So let's go back through. What we had was 1/2 times base times height. So of that pink triangle here, because this is the smallest area or the biggest negative area, we have 1/2 times 1 times the tangent of x, which is the tangent of x over 2. And then we already know that's less than or equal to x over 2. I'm just going to write it in simplified form, right? Because that's the area of this sector here. We already simplified that earlier. And then that's less than or equal to the area of this blue triangle, which is 1/2 times 1 times the sine of x. So the sine of x over 2. All right, so I'm starting in the same way I did last time, except everything's flipped. And allegedly, I'm going to end up with the same thing. So let's see how that works out. I can multiply everything by 2, and I get the tangent of x is less than or equal to x is less than or equal to sine of x. And then remember, what I also want to do here is I do kind of want to rewrite tangent as sine over cosine, because I'm going to do the same 2 steps. I'm going to take the reciprocal, and I'm going to multiply everything by sine of x. So first, to take the reciprocal, if everything is the same sign, S-I-G-N, then I can take the reciprocal of everything and just flip the inequalities. And they all are the same sign. The tangent, sine over cosine, that's negative. The angle itself is negative, and the sine of the angle is negative. So they're all the same sign. They're all negative. And again, if you wanted to kind of play around with like, is this actually true? You can play around with some numbers like this, flip the inequality. That's our rule here. Awesome. So I'm going to, let's see, what am I doing again? Taking the reciprocal. So now we have cosine x over sine of x, and flipping the inequality here. 1 over sine of x. Now I want to multiply everything by sine of x, and here's what's cool that happens. Sine of x is now negative, so all the inequalities flip back. So when I multiply everything by the sine of x, what I get is sine of x over sine of x. Here, those cancel. I'm left with cosine of x. Here I get sine of x over x, which is what I want. And then here I get sine of x over sine of x, which is just 1. And all of the inequalities flip. So I end up back with cosine of x is less than or equal to the sine of x over x, which is less than or equal to 1, which is exactly what I wanted to show. Okay, so when we're having negative angles down here in the 4th quadrant, our first inequality starts out flipped from when we have positive angles, but we flip again when we multiply both sides by the sine of x, and so that's where we end up back with this inequality that we want to show. Okay, so 2 different ways to prove this negative angle part. One, arguing that these are all even functions, their outputs for negative numbers are the same, and the other using this similar geometric argument that we used for the positive angles. So let's put our entire proof together, and what we've done is we've just proved that this inequality holds for all x in this union of intervals, which are near 0 but not necessarily at 0 itself. Okay, we just proved that. So if we were like turning this in as a paper, we'd probably want to put that at the beginning and say, hey, here's the proof for this. Once this is proved, the proof for our broader statement that this limit is 1 just falls out, because we can say this is true and these 2 limits are each 1, and so therefore by the Squeeze theorem we have that this limit equals 1. Awesome. Hopefully that proof made some sense. The second one takes significantly less time, and what's cool about the proof of this trig limit is that we actually end up using that the limit of sine of x over x equals 1 in the proof, which is kind of cool. So pretty straightforward. Here's what we're going to do. We're going to write the limit as x approaches 0 of 1 minus cosine x over x is equivalent to this other limit. We're going to multiply the numerator and denominator by 1 plus cosine of x, so we can use a Pythagorean identity. So let me go ahead and write that out. So here we go. These two limits are in fact equal. I multiplied by 1 plus cosine x over 1 plus cosine x. And if you're really observant and good with limits, you're probably like, hey, wait a minute, you introduced some discontinuities here. When you're multiplying by stuff with x in it in the numerator and denominator, we have the potential to do that. And that's okay. We introduced removable discontinuities. We created holes in the graph. So if we ignore the limit as x approaches zeros in each of these, and we try to say these expressions are equal, that's not true, because this expression is undefined in places where this is defined. However, when we have this limit notation out in front, it is true that their limits are equal. It's okay to introduce removable discontinuities that does not affect the value of the limit. Pretty cool. All right, here's what we can do in the numerator. We can multiply out 1 minus cosine times 1 plus cosine, and then we're going to use a Pythagorean identity. So let's go ahead and do that. All right, so what I did is I multiplied 1 plus cosine times 1 minus cosine out, and I got 1 minus cosine squared of x. And now I'm using this Pythagorean identity that the sine squared of x plus cosine squared of x equals 1. And if we isolate sine squared of the angle, we get that that equals 1 minus cosine squared. So I'm replacing 1 minus cosine squared with just sine squared. And now what's cool is I can actually break this expression up. Let me show you how this works. I can break it up into the product of two fractions multiplied together. All right, so I've just broken this expression up. If I multiply these things together, I get right back to where I was. And now I can apply our limit law, which says that the limit of a product is equal to the product of the limits. So let me break up this into two limits. All right, so what I've just done is I've broken this up into the product of two limits. And look here, we have this limit, which we just proved was equal to 1. Okay, so we know that this limit equals 1, and we can actually find this limit using direct substitution. The sine of 0 is 0, and 1 plus the cosine of 0. The cosine of 0 is 1, 1 plus 1 is 2, 0 over 2, which is 0. So what we can say is that this limit is equal to the product of these two limits, which is equal to 1 times 0, which is 0. If I had a little more space, I'd write out a more formal conclusion, but this limit's 1, this limit's 0, 1 times 0 is 0, so this entire thing equals 0, which is all equal to this original limit that we started with here. So we can conclude by saying that this original limit is in fact 0, and all we did was some kind of tricky algebra here, and then we used the fact that the limit as x approaches 0, the sine of x over x equals 1, which we just proved a couple minutes ago. Awesome, I had fun making this video. I hope you learned something. This is really cool stuff. Leave a comment if you have questions. Like the video, subscribe to all that stuff. Most importantly, keep flexing those brain muscles. I'll see y'all later.